800 feet, lava shooting straight into the sky, not a slow ooze, not a gentle flow, a violent, roaring fountain of molten rock blasting upward taller than the Eiffel Tower. And guys, that was just episode 44, because episode 45 is already building right now as you are watching this. And when I tell you what the pattern looks like across all 44 episodes, when I show you what the data is revealing about the acceleration of this eruption cycle, you are going to understand why volcanologists are not just watching Kīlauea right now. They are watching it very, very closely because something has changed. Something in the rhythm of this volcano has shifted, and the shift is not subtle. So let's get into this completely. Let's talk about what just happened at Kīlauea, what is happening right now, and what the pattern emerging from this eruption sequence is telling scientists about where this is heading. Because this is one of the most extraordinary volcanic events unfolding on Earth today. And most people have no idea how significant it actually is. Let me start with episode 44, because the numbers from episode 44 are, and I want to use accurate language here, exceptional. The lava fountains that erupted from the Halema-Uma'u vent complex within Kīlauea's summit caldera reached heights of approximately 800 feet, that is roughly 240 meters. For context, the Eiffel Tower in Paris is 330 meters to the tip of its antenna. We are talking about lava fountains reaching nearly to the observation deck height of one of the most iconic structures ever built by human beings. Except, this is not steel and iron. This is molten rock at approximately 1,170 degrees Celsius. That is around 2,140 degrees Fahrenheit. Being blasted into the air by volcanic gas pressure from deep within the Earth. The fountaining during episode 44 was among the most vigorous observed during this entire eruption series. Lava output rates were extraordinary. The volume of material erupted in a single episode was significant enough to measurably change the floor elevation of the crater. And then, as has happened after every previous episode in this series, the eruption paused. The fountains died, the lava retreated, the surface crusted over, silence, but not the silence of a volcano going back to sleep, the silence of a volcano recharging. And here is what I need you to understand about that recharge, because this is the heart of the story. Further in this video, I'm going to explain exactly what is driving these episodes and why the pattern of acceleration is scientifically alarming in the most fascinating possible way. But first, let me give you the full context of what this eruption series actually is, because this is not a new eruption in the traditional sense. Kīlauea's current eruptive activity at the summit began in December 2024, and since then, it has not been a continuous, steady eruption. It has been episodic, meaning the volcano erupts violently for a period of hours, then pauses, then recharges, then erupts again. Each individual burst of activity is called an episode. And by the time episode 44 concluded, the USGS Hawaiian Volcano Observatory had documented 44 of these eruptive pulses, 44 episodes, each one a separate violent eruption event. Now, when scientists step back and look at all 44 episodes as a data set, when they map the timing and the intensity and the duration, a pattern emerges. And that pattern is what is making this eruption so scientifically significant. The repose periods, the quiet intervals between eruptions, have been changing. In the earlier part of this eruption sequence, the pauses between episodes were longer. The volcano would recharge for a longer period before erupting again. But as the sequence has progressed, something has shifted. The repose periods have shortened. The episodes are coming faster. And in several cases, the intensity of the fountaining has increased. Volcanologists describe this kind of pattern as episodic eruption acceleration, and it raises a question that is genuinely important. What does it mean when a volcano that is already producing extraordinary lava fountains starts doing it more frequently? What is happening inside the volcanic system to drive this change? Let me explain the mechanism, because this is where it gets deeply fascinating. Kīlauea is a shield volcano fed by the Hawaiian hotspot, a mantle plume, a column of anomalously hot material rising from deep within the Earth's mantle, punching up through the oceanic crust of the Pacific Plate and delivering enormous volumes of magma to the surface. The Hawaiian hotspot is one of the most productive volcanic systems on Earth in terms of sheer magma output, and Kīlauea sits directly over the most active part of that system. The magma that feeds Kīlauea rises from depth into a shallow summit magma reservoir, a storage system of molten rock sitting a few kilometers beneath the surface of the caldera. As fresh magma enters from below, it brings dissolved volcanic gases with it. Carbon dioxide, sulfur dioxide, water vapor. Under the high pressure of depth, these gases stay dissolved in the melt. Think of a sealed bottle of carbonated water. The CO2 stays dissolved as long as the pressure is maintained. But as the magma rises into the shallower reservoir, the pressure decreases. The gases begin to exsolve. To come out of solution, they form bubbles, and as the gas bubble content of the magma increases, the buoyancy increases. The magma wants to rise. It forces its way up through the conduit system. It reaches the vent, and it erupts. The violence of the eruption, the height of the lava fountains, is largely controlled by how gas-rich the magma is at the moment it reaches the surface. High gas content, explosive, high fountaining eruption. The 800-foot fountains of episode 44 tell you that the magma reaching the vent was extraordinarily gas-rich. Now here's the critical question. Why are the episodes coming faster? There are several hypotheses that volcanologists are actively examining. The first is that the shallow magma reservoir is being replenished from depth at a higher rate than earlier in the eruption sequence. More magma arriving from the mantle plume, more gas-rich material entering the system. Shorter recharge time required before the next episode. The second hypothesis involves changes in the geometry of the conduit system. As repeated episodes of high fountaining activity occur, the vent and conduit system can be physically modified, widened, cleared of obstructions, made more efficient at transmitting magma from the reservoir to the surface. A more efficient conduit means faster recharge to eruptive pressure. The third hypothesis, and this is the one that I think is most important to understand right now, involves the pressurization state of the summit reservoir itself. If the reservoir is maintaining a higher baseline pressure between episodes, if the system is not fully depressurizing during each repose period, then each subsequent episode can begin from a higher starting pressure, which means faster escalation to eruption conditions, which means shorter repose periods, which means accelerating episodic frequency. And guys, when I looked at the deformation data from the USGS Hawaiian Volcano Observatory, the GPS measurements showing how the ground surface around Kīlauea's summit is moving, the picture is striking. The ground inflates as magma fills the reservoir. The GPS stations measure the surface rising. The ground deflates during eruptions as magma drains from the reservoir. The GPS stations measure the surface dropping. In the earlier episodes of this sequence, the ground was reaching full inflation before eruption. The system was fully pressurizing between events. But in more recent episodes, the inflation pattern has shown that eruptions are initiating at higher and higher baseline levels. The system is not fully relaxing between events. It is like a spring that is being compressed more and more with each cycle. And that right there is why volcanologists are paying such close attention to Kīlauea's summit right now. Let me tell you something I found in the historical record, because this is important context that changes how you see the current activity. This is not the first time Kīlauea has produced episodic, high fountaining eruptions. Between 1969 and 1974, the Mauna Ulu eruption on Kīlauea's East Rift Zone produced a series of episodic high lava fountain events. Between 1983 and 1986, the Pu'u'oro eruption on the East Rift Zone produced 47 high fountaining episodes. Episode 47 of the Pu'u'oro sequence reached fountain heights of over 2,500 feet. That is over 450 meters, nearly half a kilometer of lava in the air. And after episode 47, the character of the Pu'u'oro eruption changed fundamentally. It transitioned from episodic high fountaining to a continuous effusive eruption. A steady lava flow eruption that lasted, with only brief interruptions, for 35 years. 35 years of continuous eruption. That lava flow eventually reached the ocean. It added new land to the big island of Hawaii. It destroyed communities. It buried homes. It covered roads. For decades. Now I am not saying the current summit eruption sequence will follow the exact same trajectory. Every eruption is different. The summit location is different from the East Rift Zone. The geometry of the system is different. but the pattern of episodic high fountaining followed by a potential transition to sustained eruption is a documented pattern in Kīlauea's behavioral history. And we are currently at 44 episodes. The Pu'u'o'o sequence transitioned at episode 48. I am not drawing a direct comparison. I am telling you what the record shows, and I am telling you that the scientists at the USGS Hawaiian Volcano Observatory are absolutely aware of that record, because their job is to know exactly what this volcano has done before. So where does that leave us with episode 45? As of the latest monitoring data, the indicators at Kīlauea's summit are showing the classic pre-eruptive pattern. Ground inflation is underway. The GPS stations are measuring the surface rising as the shallow reservoir refills. Seismicity is at the elevated background level, consistent with magma movement. Sulfur dioxide emissions, a direct indicator of magma degassing at depth, are at levels consistent with active magma supply. The tilt meters, instruments that measure tiny changes in the slope of the ground surface around the summit, are showing the inflationary tilt that precedes eruption. Every instrument on that volcano is telling the same story. Episode 45 is loading. Now, let me talk about what this means beyond the immediate spectacle, because Kīlauea's summit eruption is not directly threatening populated areas right now. The eruption is confined within Halemaumau crater, which sits within the larger Kīlauea caldera, which sits within Hawaii Volcanoes National Park. The immediate hazard to communities is not lava inundation from this eruption, but there are hazards that the USGS is actively monitoring and communicating. The first is volcanic air pollution, called VOG, volcanic smog. When Kīlauea erupts, it releases enormous quantities of sulfur dioxide. That SO2 reacts in the atmosphere with oxygen, water, and other compounds to form a mixture of sulfuric acid droplets and particulate matter. This VOG blankets large areas of the Big Island depending on wind direction. It is a respiratory hazard. For people with asthma, heart conditions, or other respiratory issues, VOG exposure during high activity periods is a serious health concern. During the peak fountaining of episode 44, SO2 emission rates reached extraordinary levels, thousands of tons per day. The VOG impact extended across wide areas of Hawaii. The second hazard is lays. If lava reaches the ocean, the interaction of molten rock with seawater produces a toxic plume of hydrochloric acid and volcanic glass particles. The current summit eruption is not producing ocean entries, but as the crater floor rises with accumulated lava, the geometry of the system changes, and the history of Kīlauea includes multiple periods where summit activity eventually connected with rift zone activity. The third and most significant longer-term hazard consideration is the rift zones themselves. Kīlauea has two major rift zones, the East Rift Zone and the Southwest Rift Zone. These are the structural weaknesses extending from the summit like cracks in a windshield. When the summit reservoir becomes sufficiently pressurized, when the magma has nowhere else to go at the summit, it can intrude into the rift zones. And when magma intrudes into the rift zones and reaches the surface, it does so far from the protected caldera environment, it does so in areas that are closer to communities. The 2018 eruption. Guys, I have to talk about 2018, because 2018 is what everyone working on Kīlauea carries with them. In 2018, after a period of significant summit activity, the Kīlauea system experienced a dramatic shift. Magma drained from the summit reservoir and traveled down the East Rift Zone. The summit caldera floor collapsed catastrophically. And in the lower East Rift Zone, in an area called Leilani Estates, a residential community, the ground opened up. Fissures cracked open in people's backyards, in their streets, between their homes. Lava erupted at extraordinary rates from these new fissures. The 2018 eruption ultimately destroyed over 700 homes. It buried entire neighborhoods under 30 to 80 feet of lava. It covered nearly 14 square miles of land. It added approximately 875 acres of new land to the Big Island where the lava entered the ocean. And it happened with a speed and a violence that shocked even the scientists who monitor this volcano for a living. The people who lost their homes, the people who watched lava pour down their streets. They had days to evacuate, not weeks, days. And the trigger for all of that was a period of intense summit pressurization, a period that in some ways rhymes with what we are observing right now. I am not predicting a repeat of 2018. The USGS has not indicated that rift zone intrusion is an immediate concern at this time, but I am telling you what the record shows. And I am telling you that the scientists monitoring this system right now are not casually watching. They are watching with the full memory of 2018 behind every instrument reading. So what do we watch next? What are the signals that would indicate this eruption is escalating towards something more significant? First, watch the summit deformation data. If the inflation rate at the summit accelerates significantly, if the GPS stations start measuring rapid ground rise, that indicates increasing magma pressure. The USGS HVO publishes this data publicly in near real time. Second, watch for signs of rift zone unrest. Increased seismicity along the east rift zone or southwest rift zone. Ground deformation along the rift corridors. These would be early indicators of potential magma migration away from the summit. Third, watch the SO2 emission rates. Higher SO2 means more magma degassing. More magma degassing at shallow levels means more magma near the surface. The emission rate trend over successive episodes is a key indicator of system pressurization state. Fourth, watch the episode repose intervals. If the time between episodes continues to shorten, if episode 45 begins significantly faster after episode 44 than episode 44 began after episode 43, that acceleration data point is critical. Fifth, watch for any reports of ground cracking or unusual activity outside the caldera, particularly in the Kīlauea Desert to the southwest or in the Upper East Rift Zone areas. These would be among the earliest surface expressions of rift zone pressurization. The USGS Hawaiian Volcano Observatory publishes daily updates. Their monitoring network on Kīlauea is among the densest and most sophisticated volcano monitoring systems in the world. These are the people who are on the pulse of this. And right now what they are observing is a volcano in an accelerating episodic eruption sequence, approaching 45 episodes of high fountain activity with elevated baseline system pressure and episode 45 already loading. Guys, I have to say this. Kīlauea is the most monitored volcano on Earth. The science watching this mountain is extraordinary. The warning systems are real. They are sophisticated, they work. But 2018 taught everyone something important. Kīlauea is also a volcano that can surprise you, that can transition from one mode of behavior to a completely different and far more impactful mode with a speed that compresses your response time to days. The residents of Leilani Estates in 2018 did not expect to be packing what they could carry into a car and leaving their homes behind. And that is why what is happening right now at Kīlauea's summit matters beyond the extraordinary visual spectacle of 800-foot lava fountains. The spectacle is real. The beauty of it is real. But the system driving it is also a system with a documented history of dramatic and destructive transitions. 800-foot fountains, 44 episodes. Episode 45 loading, the pattern accelerating. This is a story you watch, not from inside the hazard zone, but you watch it because this is a living, breathing planet doing what it has done for billions of years. And right now it is doing it in one of the most spectacular and scientifically significant ways that modern volcanology has ever had the instruments to observe. Stay safe, guys. Be aware. Bye-bye.